This presentation is delivered by the Stanford Center for Professional Development.
The piece I need is not here, so I'm going to actually just talk to you about what it says on my slides, and then when Jason arrives, right, we'll plug it back in and we'll see what's going on. Oh, there's Jason, there we go. So what I'm going to do today actually is something kind of fun. Is I'm going to take a case study of a particular data structure design, and the one I'm looking at here is the lexicon. So how many of you actually ever decided to just open up the lexicon file just to see what was in there at some point during the quarter? We used it a couple times. Anybody want to tell us what they learned by opening up that file? Anything interesting? It's a data structure called a dog. You're like, well, that's a pretty funny name for something. Was the code particularly well commented, particularly easy to read, easy to understand? No. Who wrote that code? She should totally be fired. Yeah, so that's some code I wrote kind of a long time ago, actually, to solve this particular problem. And actually, I would like to talk you through kind of how it is I came to discover the dog and why it is the dog was the choice that made sense for what the need pattern we had for the lexicon was. So let me just refresh what the lexicon does, right? It is a special case of kind of set or map. It is a container, right, where you're going to stick things in. They're going to be unique, right? There's no need for any sort of duplicate. The keys are always strings, and in fact, they're English words. And that's going to be an important thing to remember, that they're not just arbitrary sequences of letters, right? They have certain patterns to them and certain sizes that might actually be something we could capitalize on. When we know something about the domain, right, we may be able to kind of special case or tune our data structure to solve that problem very well in particular. It has no associated values. It doesn't have dictionary definitions or synonyms or anything like that, right? So it really just exists or doesn't exist. That we were interested in supporting, and it also has, in addition to the kind of being able to add words and check if a word is contained, there's also this prefixing operation that we had talked a little about in Boggle, and that came back on the midterm. Like, why was prefixing important, right? It was critical for pruning these dead-end paths, right? These searches on the Boggle board that otherwise, right, would really have taken a lot of time and kind of led to nothing of any value. So what I'm going to talk you through is some of the obvious choices based on data structures we already know about, and see where they would go. So this is a thought experiment. It's not that I wrote all these to find out. Actually, I mostly did a lot of this on paper, trying to figure out what options we had and how they would play out and what kind of trade-offs I'd have to make them work. So the simplest case, right, of any kind of collection is to think about whether vector or array can do the job for you. In this case, having a vector that's kept in alphabetically sorted order seems like a pretty good, easy way to get this thing up and running, and how would it behave. So in order to do a contains word on this data structure, what algorithm are you going to use to do your searching? Binary search, right? It's in sorted order, right? We've got to take advantage of that, right? If we do a linear search, I'm looking for the word mediocre, I'm going to be trucking through, thousands of words before I find it. So definitely I want to be using binary search, equals, comparing my strings, less than, greater than, dividing in half, and so it should run a logarithmic time. Logarithmic time, right, one of those great performers that you learned in the PQ assignment, hopefully it's just basically not measurable on today's computers. So even for entries of 100,000, 500,000, right, basically for free. How do we do contains prefix? Can we also do a fast prefix search given this data structure? I hope so, right? Thinking about the same kind of binary search. In this case, though, looking at substring, right? So comparing if I'm looking for a 3-character substring, only looking at the first 3 characters, decide which way to go. Once I find something that matches in the first 3 characters, I'm done. So again, still using the sorted property to quickly narrow in on where it could be. When it's time to add a new word to this, so someone asks me to put in the word abalone, I got to use that binary search, right, to find out where to go. So in logarithmic time, I can tell you where the new word goes. But then to put it into position, there's going to be some shuffling. And that's where this operation starts to bog down, given the idea that you might be moving half or more of your items on average to make that space for that one to open up. It is going to require a linear time operation to get new words into the data structure. Okay. Probably still, though, a reasonable approach, right? These are the operations that get done, immense numbers of times in Boggle, right? You're doing a ton of contains words and contain prefixes as you're exhaustively searching that big board. But the adds are done kind of once at the beginning. You build that big dictionary, and then you subsequently use it. And so if it took kind of a little bit more time to build that thing, sort of an n-squared operation to kind of load it up, well, maybe that would be okay. The other thing we're going to look at is space usage, and that's, and some of this is a little bit of an interesting artifact of the time I was working on this. It turns out space was actually really a limiting factor in what we had available to us in terms of core memories of our machines and what we could take up for our dictionary. In this case, it has per entry the size of the string, which we don't exactly know how the string is represented, right? It's an abstraction to us, but we can make the assumption, kind of a simplification, that it's probably about the length of the string times the size of a character. And there might be a little bit more housekeeping associated with it, but that's a pretty good estimate of what it's taking. So in fact, it's the string data itself that's being represented in this vector without much else overhead, right? So if we say words are average about 8 characters, about 8 bytes per word. So if we had 100,000 words, we expect to have 800,000 bytes invested in this sorted vector arrangement. Excess capacity, a couple other things that kind of might tweak that a little bit, but that gives us at least a good starting point to think about how this compares to alternatives. Okay, so then if we said, well, we know that sortedness, right, that binary search is the real advantage of keeping it in sorted order, but the contiguous nature of the array kind of bites us in terms of insert. If we reorganize into that binary search tree to give ourselves the dynamic flexibility of wiring in the left and right halves through pointers as opposed to contiguous memory, then we know we can also get add to run in logarithmic time. So looking at these operations, contains word right is a tree search that's using equals equals left right deciding which way to go, and also performs logarithmically if the tree is balanced. Contains prefix, same deal. In this case, looking at the subster, working our way down, knowing which way to go. And then add can also perform in logarithmic time because it does the same search, right? Falling off the bottom and then inserting the new word there or finding it along the way and not having any work to do. So we can get all our operations down to logarithmic time, which we know to be kind of fast enough to actually not be worth fighting any harder for. Where did we pay for this? Nothing really comes for free, right? Overhead, right? And overhead in this case, memory, right, is certainly one of the places, right, where there's going to be a pretty big cost, right? That we now have the string data for each entry plus a left pointer and a right pointer, and if we're doing the work to keep it balanced, which we probably ought to do if we want to avoid the degenerate cases of it kind of getting totally out of whack and degenerating into linear time, we're going to have a couple more bits, bytes thrown into that factor too. And so if we're assuming that there's 10 bytes of overhead, 4 bytes in each of these plus another 2 for the balance factor, right, then we've added 10 bytes of overhead on top of the 8 bytes for the word. Getting a little bit hefty. Something to worry about. Also, in terms of code complexity, which I didn't put a bullet up for, but it's also worth kind of weighing it in your mind also, which is that building the fancier, more complicated data structure probably meant you spent more time debugging it, more time developing it, right? It will be harder for someone later to maintain and deal with because it's actually just more complicated code. That somebody looking at a sorted vector isn't likely to actually, like they want to add a new operation, let's say they add remove. You're able to take a word out of the lexicon doesn't currently support that. Somebody adding that on the sorted vector implementation probably won't find themselves too tripped up. Someone who has to do a remove out of a binary search tree, removing it and reattaching the subtrees and not destroying the balancing, right, is a pretty complicated operation. So we've invested in this data structure that actually will keep on, right, creating further development hassles for any modifications that are down the road for this data structure. So it is a big investment in your brain power to keep it working. So let's think about what a hash table could do for us. The hash table was the last thing that we looked at on Friday, kind of just moving away from this whole idea of sortedness and kind of moving it out of band to this idea of a hashing function. So if I have a hash table that has a certain number of buckets, that uses a linked list for chaining to handle the collisions, right, then what I would have is my words just scattered around my table, allowing me to have quick access by hashing to the right bucket and then working my way down the bucket to C. So the contains word would do a standard hash table lookup. Take the word, mediate, run it through the hash function. It says, oh, it's bucket 3 in this case, right? I go to bucket 3, I walk down the linked list, I find it or not. I can tell you whether the word mediate, if it's in the table, had to be in bucket 3, no questions asked. In that case, right, the expected time for that is going to be n over b, where n is the number of entries, b is the number of buckets. If we have buckets set to be in the rough order of the number of entries, then we're going to get constant access there. Now I want to do contains prefix. How do I do this? I want to know if there's any words in this table that begin with med. where do I look? If I run MED through the hash function, do I expect that I would get the same number as other words that begin with MED, like mediate and median and mediator? You say yes. All right, let's take that to its extreme. If I expect that if a prefix and any longer words all hash to the same thing, then should it be the case, for example, like think about the simplest case of a prefix, M. Should all the words that begin with M hash to the same place? If they did, we're in trouble, right? If all prefixes did hash to the same place, then what I'm going to end up with is a really heavily clustered table where A, B, C, Z, there's 26 buckets that have all the Z words, all the Y words, all the whatnot, and none of the other buckets would be used. Right? So in fact, actually, as part of the good behavior of a hash function, we're hoping that actually it does jumble things up, and that a word that looks like one but has another letter added on the end, we're hoping it goes somewhere totally different. That median and medians hopefully go to two totally disparate places. That if there were patterns where words that were substrings of each other all got hashed to the same locations, right, we would end up with heavy clustering, because there are a lot of words that repeat parts of the other words in the dictionary. So in fact, if I want to know if there's any words that begin with MED, I have no a priori information about where to look for them. They could be anywhere, right? I could hash MED and see if MED itself was a word, right? But let's say it was something that itself, like was just the beginning of something, ST, STR, right? There's a lot of words that begin with that, but STR itself is not a word. So hashing to that bucket and looking for it would only tell me if there's exactly STR, and then occasionally there might be some STR words also there. But other than that, right, we just got to look. And where do we look? Everywhere. Everywhere, everywhere, everywhere. That in order to conclude there is no word that begins with the prefix we have, the only way to be confident of that is to either find something or to have searched the entire table and not found it. And so it does require this completely linear, exhaustive look through the entire contents of the hash table to know something, for example, is not a prefix. You might find one quickly, so in the best case, right, you might be in the first couple buckets, happen upon one. But no guarantees overall, and certainly when it's not a prefix, right, it's going to require a complete look-see of everything. That's kind of a bummer. Adding a word, back to the fast behavior again, hashing the bucket, checking to see if it's already there, adding, if needed, N over B. So it gets good times on these two, but then kind of really bottoms out when it comes to supporting that prefix search. Its space usage is kind of roughly comparable to that of the binary search tree. We've got the string data itself, and we've got the 4-byte pointer on the linked list cell. There's also the 4-byte bucket pointer, which is over in this other structure here, this array full of buckets. If that number, though, is roughly equal to the number of cells, then you can kind of just count it as, well, each entry had this 12-byte cell plus a 4-byte bucket pointer somewhere that you can kind of think of as associated on a per entry basis to tell you it's about, 8 bytes of overhead on top of the string. So 16 bytes, right, for each entry in the table. Okay. That's what we have so far. We've got pretty good performance, right, on contains word no matter what we choose, right? We can get either logarithmic or constant time with either of these 3 data structures, right? So perfectly acceptable performance there. We cannot get contains prefix to run well in a hash table. Just doesn't happen, right, the way hashing works. And then add, right, can be fast on the 2 complicated pointer-based data structures to the right, but can't be fast on the sorted vector. And then we see kind of some trade-offs here in terms of space versus time, right, that there's very little space overhead in the sorted vector case, right, but that really blossoms, right, into 2 times, almost 3 times, right, the storage, right, needed in the BST and hash table case. The code also got a lot more complicated when we moved up to those data structures. So then I'll tell you actually that it turns out that the runtime performance was interesting to us when I was exploring this, but in fact actually more important at the time was the memory usage. That the memory usage, right, was really the big obstacle that we had. The official Scrabble Players Dictionary 2 is actually the source for the word list that we're using. It has about 128,000 words, I think is exactly the number it has. And the average length of those is 8 characters, and the file itself is over a megabyte. So on disk, if you were just to look at the listing of all the words, right, it's a megabyte, a little over a megabyte there. If we were loading it into the sorted vector, we'd get something that was just roughly equal to that. It would take about a megabyte of space plus a little bit of noise. The ones that double up that, right, take it up to 2.5 megabytes total. At the time, right, we were working, and I know this is going to seem completely archaic to you, but we had these stone tablets that we worked on. And they typically had main memories of about a megabyte, maybe, like in a exciting case, 4 megabytes, 4 whole megabytes of RAM. So it was not possible, right, that we could dedicate 1 or 2 megabytes of your main memory to just your lexicon. It just wasn't, there just wasn't enough space to go around. So we're working in this very tight environment in terms of that. So it's a little bit more like, for example, today's world of embedded devices. If you're writing something for an iPod or a cell phone, you have a lot less gargantuan memory. So your average desktop machine having a gigabyte of RAM now, you're like, yeah, whatever, a megabyte here, 10 megabytes there, free, all the memory you want. And so this seems kind of like a silly thing to focus on, but this was 1995, and it turns out, yeah, there was certainly more interest in keeping it tight to the memory. The Boggle lexicon that we have actually takes under 1/3 of a megabyte. The memory it's used while it's working and searching and checking for words and prefixes is actually smaller than the on-disk form of the data we started with. So it actually does kind of a bit of a compression as part of its strategy for storage, which is pretty interesting to think about. So I'll tell you actually the truth about how we first did Boggle, because it's kind of a little interesting historical perspective on it. That Boggle was given by a colleague of mine for the first time, Todd Feldman. He was the guy who came up with the idea, which is a great idea. And he said, oh, this is a great assignment. And when he wrote it, he said, oh, I need a lexicon. So as part of kind of putting the assignment together, he was like, oh, we have to get some lexicon. So he looked around and he found a word list that had about 20,000 words. And well, I think we first found this word list and we said, oh, it's just impossible, right? It's going to take, a megabyte or more, and we just don't have that kind of space. So we need a much smaller data file. So we had a data file that had about 20,000 words, right, which then takes about 200K. And he actually wrote it using a hash table. So given he wrote it as a hash table, he just didn't support contains prefix. Just didn't put it in. And because you can't do it efficiently. So it actually took, a smaller amount of space, it had a smaller word list, and it wouldn't do contains prefix. So then people wrote Boggle. And as you learned from that midterm question, like, you can write Boggle without contains prefix. It spends a lot more time looking down these dead ends, but it eventually bottoms out, right, when it runs off the board and uses all the cubes. And it actually, in some ways, almost made the program a little bit more satisfying to write in one odd way, which is when you were, so it's the computer's turn, right, that uses the prefix pruning. So you would type in your words, and it would be perfectly fine finding them. It doesn't use the prefix part when it's doing the human's turn. You're typing your words, it's finding them. You're typing the words, it's finding them. Then you would go to do the computer's turn, and you'd say, okay, go, and now it would take a really long time. It'd be hunting around the board. Oh, it'd be working so hard. Your fan would be coming on, right? Like you'd feel like, oh, my computer's doing something. And then it would show up with twice as many words as you found, or 10 times as many words as you found, or whatever. And in fact, then you would say, well, at least it had to work hard to beat me, right? And then you felt like, I wrote this program that causes my processor to get busy, right? I felt good. And in fact, actually, the word list was pretty small. So in fact, it wasn't even actually as likely to beat you because it didn't know as many words. 125,000 words is an enormous number of words. The average, it's been, I've heard different factors on this, but the average person's vocabulary, English vocabulary, is about 20 to 30,000 words. It tends to be about 10,000 higher if you've gone to college, so maybe 30 to 40. The fact that it knows 80,000 more words than the average college graduate means it knows a lot of obscure words too. And so in fact, it not only does it very quickly find all those words and then produce these ridiculous words that I've never heard of, right? It's almost like it's taunting you by doing it in a millisecond. And back then, it took a while. So it was actually like, okay, well, it beat me, but it had to work hard. But then, so then I took over Boggle. I taught X maybe a quarter or two later, and I said, oh, I'm gonna write a lexicon. I'm gonna go off and make a little project for myself because I don't have enough work to do. And my goal was to make one that would do prefix, but that also would be tight enough on memory that we could actually load a much bigger dictionary file, because I thought it'd actually make the game even more fun to play. All right, so here's where I started. This is a little excerpt from the middle of the dictionary. STRA, yeah, that's certainly the thing you notice, right? When you look at this thing, you see straddle, straddle, straddler, straddler, straddle, straddling. And there are these words in here that you can't believe you're allowed to do this. But apparently you can put like ER and IER and IES and ING and on almost anything out there, and it makes a valid word. And so, although, you never really thought about the fact that straightforward, straightforwardly, straightforwardness, right, are all there, there is a huge amount of repetition. And this is where I said we're going to use some information about the domain. These aren't just arbitrary strings. They're not just random sequences of letters, right, that are, picked out of the air, that they develop over time. There's, word roots, right, there's suffixes, right, there's these prefixes that mean things that actually show you that looking at this, little excerpt out of the middle, there's an awful lot of words that repeat portions of other words. And that may be part of what we can capitalize on, that instead of really recording straight away and straight away is repeating those first 11 characters and adding an S, is there some way that I can unify the data that I have here? The same way when we try to find code, you have the same passage of code repeated 2 or 3 times. We're always saying, unify it, move it into a helper and call it in 3 places. It's like, can we do the same thing with our data? Can we share the parts of the words that are in common and only distinguish where they are different? So take a look at this. This is a little portion, right, of something called a trie. So a trie is spelled T-R-I-E, and it's actually from retrieval, but sadly it's still pronounced trie, just to confuse you. And it is a variant of a tree. And in this case, it's a tree that has 26 children coming out of any particular node, 1 for each letter of the alphabet. And so starting from the root node at the top, all the words that begin with A are actually down the A branch, and then there's a B branch, there'd be a C branch and a D branch, and so the idea is that all the words, like if you think of the levels of the tree, are actually like, these are all the 0th characters of the word, and then that second level is all the characters that follow that 0th character. So here's the AB words and the AC words and the AX words. Over here is the ST words, but there's not an SX, right? So there's some places that actually aren't filled out in this tree. And as you keep going down further, so that the depth you would trace through a tree would actually be tracing through the characters in sequence that make words. And so in this form, right, tracing out a path through this tree from the root down to a particular node tells you about prefixes. So there are words that begin with A and words that begin with AC and ACE. And then there's actually a little notation here that's done by a visual of the bold and circle around it that says, oh, and the path that led here from the root is a word. So A is a word, and ace is a word, and aces is a word. Act is a word, and so is acted and actor. And in this case, the act part, right, is totally shared. So everything that comes off of act, acting, acted, actor, actors, can all share that initial part. And for a word like act, it doesn't seem that profound, but you start thinking about words like strawberry or straightforward or stratosphere and realize that stratospheric and strawberries and straightforwardly, right, can all leverage the other 10 or 12 characters, right, that were already invested in the root word, and that straightjacket and straightforward can even share straight, that there's actually a lot of prefixes, right, that can be unified across the space of the dictionary. So knowing that words have these patterns, right, helps us to do this. So let's build that. So the first form of this, and this again is a thought experiment. I did not actually write it this way because it would just be absolutely astronomically expensive, but it was a good way to kind of think about where I needed to go, was I designed a new kind of trie node that had the letter and a little Boolean flag of is this the word, so whether it had the dark circle around it, and that had a 26-member children array, so pointers to other nodes like this one, so totally recursive, starting from that root, and then the idea is to use those 26 children as A being in the first slot and Z in the last slot to make it really easy to kind of just trace letter by letter down to the levels of the tree. So I'd have this one root node that pointed to the initial one, and then all the words that begin with A are off that first slot, all from Z off the last slot. So when I want to know if a word is in the dictionary, what do I have to do in this data structure? How do I find it? I want to find the word, far. Where do I look? Left, right, down, which way? It'd be great if you tell me that I know you'd understand what my data structure is. Yeah. Exactly. So at the very top I say, okay, F's my first letter. Match my F, get me to the F node, and now it says recursively find AR from here. So it's very recursive. It'll be like find the first letter and then recursively find the substring from here working down. So find an A out of the next node, find an R out of the next node, and then when you get to that node, you'll check this little is word Boolean and say, okay, was that path I traced marked in the dictionary as leading to something that's known to be a word? The prefix looks exactly the same except for that last check for the as word. So given that nodes exist in this because further down there are some words, I just trace out a sequence of letters, STR, and as long as there's something there, then I know that away from there are subsequent children beneath it that lead to words. And then adding a word does the same operation. If I need to add the word strawberry, right, then I start looking for STR, and at some point, right, I find some places where the nodes don't exist, and I start creating them from there on down. So it is, tracing what exists and then adding new nodes off the bottom and then marking the final one as, yes, this is a word. What's interesting about this, right, is that all three of these operations don't actually make any reference to how many words are in the dictionary. They are all dependent on the length of the word you're searching for or adding into the dictionary. If there's 10 words in there, if there's 1,000 words in there, if there's 1,000,000 words in there, right? That in no way does the big O depend on how big or how loaded the data structure is. That's kind of wacky. The longest word, according to the Oxford English Dictionary, there you go. You're not going to be making that on the Boggle board anytime soon because it's only got 16 cubes. Even Big Boggle can't really make that puppy. But just so you know, 45, not so many, right? In fact, actually, here's a little thought for you. Not only is it not dependent on num words, it actually almost has a little bit of an inverse relationship with num words, especially the add operation. That as the data structure becomes more loaded, there's typically less work to do in add. So if strawberry is in there and you go to add strawberries, then actually you already have strawberry, to depend on, and you just need to build off the thing. So the fact that the more words that are in there, the more likely that some of the nodes you already need are already in place, and then you can just kind of blow past them and just add your new nodes. So that's odd. You think of most data structures really as clearly like as they get heavier, right? It takes more work to install new things in it rather than less. Well, the thing is, they're organized by letter in that 26-member array. So in fact, I don't really have to look, right? So I just go straight to the slot. If I'm looking for strawberry, I look for S, and then I go straight to the T slot and the R slot. And so in fact, if the node was already in place, I'm not searching for it. It really just is always exactly in the R slot. That's why there's 26 of them. So each array is 26, and they're A through Z. And if there's an empty slot, we're using a null. Right, so in this case, it's optimized to make it super fast, right? I don't even have to look through the letters to find the one that matches. There's no matching. It just goes straight to the R slot, the Z slot, the S slot. We're going to see this is going to be a consequence we can't, tolerate, but it is at least the starting point for thinking about how to build a data structure. So the space usage is where this thing really, so this is an extreme example of a space-time trade-off, right? We've got this thing that optimizes beautifully, right, for like O of length of the word, right? So that means typically 8 operations, right, on average are going to be needed to add or to search for something. The space we're using here is 106 bytes per node. So that's this 26-member 4-byte array plus 2 bytes for the character and the Boolean that are up there. 106 bytes is a lot of memory. And the trie has about 250,000 nodes. So given the 125,000 words that I said are in the input, if you build them into a trie, they take about 250,000 nodes. That's an interesting sort of number to think about, though. You have 125,000 words. They take 250,000 nodes. That tells you actually that kind of on average, each word has about 2 unique nodes. That even words like straightforward and straightforwardly, kind of on average are sharing enough of their common prefix parts that there's very little unique data added by any particular word in there that average across the whole thing. That's pretty neat to know. However, this is just not going to fly. So here I was telling you that my main memory had, 4 megabytes maybe on a good day, and now I've actually, built a data structure that's going to require, 6 times that in terms of storage. Okay, we got to squeeze that down. So the first thing we can do is to realize that those 26, allocating a full 26-member array, of which I only plan on using some of the slots, is pretty wasteful. So instead of saying I'm committing to 26 per thing, I'll say, well, how about if I have an array that actually is tight to the number of children coming out of this node? So the very first node will have 26. There are words that start with every letter in the alphabet. But from there, it very quickly winnows down. You have the letter X, right? You do not need the full 26 children coming off of X. There's only a few letters that follow X, right, in the English language that are going to need to be fleshed out. You need the XA, you need an XE, but you don't need XJ, you don't need XK, a whole bunch of things like that. So if I change the structure here to instead of being a 26-member array of node pointers, I make it to be a pointer to a set of node pointers. So this is a dynamic array that I'm keeping track of the number of children in a second field here. That the first one will be allocated to 26, the second one will be allocated to 8. This is going to change a little bit of our running times because now we won't be able to go exactly to the S slot. We'll have to go look for it. So on each step down the tree, it'll be looking through that sized array at this slot to find the right match. But it adds a constant factor basically on top of O of length of the word. So the space usage of this is basically we're just not storing all those nulls. And there were a lot of nulls. That the node itself is now just 10 bytes, and then there's some space in this dynamic array out there, which is the number of children times the 4-byte pointer. That on average, right, a node has 6 children across the 250,000 nodes in the data structure that's being built from this, right? So 26 was way overkill, right? About 20 of them had nulls. for most of the nodes. And many of them, for example, at the very bottom of the tree, have completely none, right? They're all null. So you get to a word, like straightforwardly, there's nothing after that Y, right? And so it has 0 children coming out the back of that one. And so certainly having 26 null children pointing away from that was a waste that we could tighten up. So when we get it down to this, right, we'll have 44 bytes, or 34 bytes, right, for the per node. Still 250,000 nodes, still 8.5 megabytes, right? So we're not winning any prizes just yet, but we are making good progress, right? That got us down like a factor of 3 or 4 right there. So I still have the same number of nodes. All I changed, right, was the pointers to the subsequent nodes further down the tree. So the kind of letters and how the letters connect to each other, the connectivity is still very much the same. It's just that in any particular node, how many children does it have, right? I was storing a whole bunch of nulls, and now I'm not storing those nulls. So the number of nodes is still exactly as it was before. So I'm going to do one other little squishing thing on this data structure, and then I'm going to kind of flip gears for a second. So still using kind of my CS side of things, how can I squash things down? I'm going to use a technique that we used in the heap. So in the case of the binary heap that we implemented into the PQ, you'll remember that we drew pictures in the handout that showed a heap with, I have a parent with 2 children, which has 4 grandchildren, and so on, but that we actually compressed that down into an array. And in the array, there was this pattern of, here is the root node. So we'll call this level 0. And then the next 2 nodes are level 1. And the next 4 nodes are level 2, and so on. And so there's 1, there's 1 here, there's 2 here, there's 4 here, there's 8 here. And we flattened it down kind of by generation, so looking at what was at the top and what was underneath it. When we did that, right, we removed all the space for pointers. That although we drew those pictures in the heap as though there were pointers there, in fact, there were not. Right? There were no pointers being stored in the heap-based version of the PQ. And so that gets us back to kind of array-like storage requirements, but by flattening it down into this array, right, and still kind of using the tree conceptually to work our way through it, right, we're getting the advantages of that traversal that's based on height of tree, not, length of vector. So if we do the same thing with the trie, it's a little bit more complicated because there were a couple things about heap that made this a little easier. The thing that heap always had 2 children, and so there were these rules about how the tree was filled in that meant you could always compute parent and child index using this kind of divide by 2, multiply by 2 exchange operation. In this case, right, what we're going to have to do is just lay it down by generation, but we don't know how big a generation is going to be, so we're actually going to have to keep track of it manually. So the root node will have all A through Z. So this would be level 1, which is A through Z here. And then level 2 is, there'd be a bunch of slots here, which is the A followed by some letter, and then there'd be the B's followed by some letter, and then there'd be the C's followed by some letter, and so on. And then further down is level 3, which are the 3-character words. So these are all the single character paths, 2-character paths, 3-character paths, kind of flattened down. And so if I look at what I changed here, my first node says it has no letter, that's the root node, it's not a word, and it says its children begin at index 1, so the next location. So it's not a multiply by 2 and add 1 or something like that. It's like, okay, here's where my children begin. They're at slot 1 in the array, and then there are 26 of them. So that means that A, B, C, D are kind of in order there. If I look at A is a word, and it says its children begin at index 27. And there are 12 of them. So there are 12 characters out of the 26 that can follow an A in the sequence of a valid word. And then B's children begin at index 39, which is 27 plus 12. So that's where the A's children are sitting here at index 27 to 38, and then 39 to, I think B has 8 or so children, right? And C, and so on. So we flattened it all down by generation into an array. That means all the space for pointers, right, has now been removed. One serious consequence of this, though, is that the pointers got us flexibility. That insert and remove was dependent on the idea that pointers really being there, pointers buying us, right, the ability to insert and delete without doing a shuffle. That now, once I have flattened it, right, I have suddenly bought back the same problems that arrays have, which is if I have the words here that have AB for abalone and AC for act, and I don't happen to have any words with AD, and now I go in and I try to add the word add, that in order to put D in there, right, we're going to have to move everything over, and then there's going to be a lot of shuffling and whatnot. So I'm starting to build a data structure that's losing some flexibility but saving space. So I'm in some sense focusing my attention on how can I build a data structure that's really fast to search, even if it was a little harder to build. Because it turns out the thing I most care about is making sure it can actually very, very efficiently look up words. Maybe building it once, being a little slow, isn't so painful. So the space usage in this gets this down to just 10 bytes per node. All the pointers are gone. So there was 24 bytes of pointers that we've just eliminated. And that means we've got 2.5 megabyte memory footprint right now. So we're kind of getting close to hitting the range for binary tree and hash table. Okay. Now I'm going to go back to the domain again. So I worked on it kind of from the CS side, thinking about things I know about data structures and reorganizing arrays and heaps and pointers. I'm going to go back and look at that domain again and see if there's something else I can kind of take advantage of. So this is a different cross-section of the dictionary showing the word adapted, adapter, adapters, adapting, adaption, adaptions, adapts. So 8 words, right, that are all built off the adapt root with a bunch of suffixes. If I look sort of over a little bit further, I've got desert, deserted, deserter, desertings, deserting, desertion, desertion, deserts. Okay, and detect, and insert, and perfect, and invent, and interrupt, that all are verbs, right, for which you can apply the past tense and the gerund form and the ions, right, that tack onto that root word to give you these suffixes. And each of these words that is shown up here has exactly the same set of suffixes that can be applied to it. So I did this thing about prefixes, right? I went out of my way to find that, so all these words could share that same prefix, assert, asserter, assertings, asserting. But is there some way I can take this idea of corrupt and assert and insert, and then once I get down to that T where they end, is there a way they can also share their back end parts? That those INGs and IONs, can they be unified as well? Well, why not? Why not? So here is the first version of what's going to be the DOG, the directed acyclic word graph. It takes the idea of unifying the prefixes and now applies it to the suffixes. That there are a lot of words that end in the same letters as well as start in the same letters. Why not just apply the same kind of unification and sharing on the back end? So here comes in adapt and adopt and based and port. And out the back end is ports and portion and porting and porter and adopter and adopted and basting and bastion, all coming off that sharing, right, all the endings, because they have the same words that are viable and the same connections that are between them. So the idea that all sharing the ER and the ER leading into the S, and that same S, for example, being shared from portion and based and adopt and adopter, all coming into the same ending of, all these things that end in S are words. Here's an S that is a word for them to share. So it is directed. So it is a graph, right? So once we remove this, the idea that there's a single path, right, from the root to any node, right, we're no longer a tree structure. So we can get to T by going through adapt or adopt or port. And so that no longer fits the definition of what is a tree. It's become a graph. We can get to these nodes from different places. The arcs go one way in this case, though we can't go back up the tree to find the words in reverse. There are no cycles, so acyclic, right? You can't just wank around some portion and get as many bananas if you want. And they have we have certain nodes that are marked in this case the same way they were in the trie for, yes, this path from the root node to here does represent a word in this situation. So building this is a little bit complicated. I'll give you a little bit of the idea of the intuition for it, and I will not get too deep into it. But largely the way you do this is you build the trie, so that it doesn't have the unification of the suffixes, it only unifies the prefixes. And then you work backwards on the suffixes. So in some sense you look at all the words that end, for example, in S in the dictionary. And you find all the ones that just end in one S that goes nowhere, and you say, well, look, this S looks like every other S in this thing. All these words that are just plurals or verbs that can have an S tacked on, let's share that S. And then you take, however many S's there were, 1,000 of them, and you say, these are all the same S. And then what you do is you look at all the nodes that lead into that S. So you're kind of traversing the graph in reverse, and you say, well, look, here's a bunch of people who lead in on an E. right? And if that E is a word or not, that there might be some group that has E that's also a word, so like the word apple and apples, but sometimes the E is not, right, where that wasn't a stopping place, let's say, for like parties, it wasn't. And so all the ones that are a word can unify on the E that was a word, and the ones that aren't are that way can unify on that, and you just work your way backwards from there. So you say, well, what letters led into that E? And so kind of from the end of the words backwards, you're looking for all the people who can end in an S and end in an E and end in an IES, and unify them up. Making sure that, right, they have kind of all the same outgoing connections. So for example, running has an ing at the end, so does swimming, but there is swimmingly and there's not runningly, so you have to be careful about unifying things that they really have to kind of have all identical properties from this point down to the bottom of the tree to be unifiable. But it's a pretty neat process. It's actually what's called DFA subset minimization. So if you want to learn a little bit about it, that's the word to look up. And so if I do that, and I build this as a dog, I'm still using the same structure definition here. But what I am doing is unifying suffixes as well as prefixes, and that actually is going to change the number of nodes that I need drastically. It goes down to 80,000 from my initial 250,000. And if you think about the number of words again, right, there were 125,000 words in the dictionary. The dog has just 80,000 words, so it means actually once you start unifying the suffixes, it's like most words don't even have, or many of the words don't even have any nodes of their own, that they are unique to them whatsoever, right? They just exist kind of as portions of other words that have all been joined together and compressed into one package. So 80,000 nodes total, about 2/3 the number of words total in the thing. So we have 10 nodes, 10 byte nodes, and 80,000 of them, right? We are down to under a megabyte. So we've crossed that really interesting barrier of the data structure on disk, the data that was fed into it, those words, was over a megabyte. And now we have created a representation that actually is compressed, that uses less space than the text file did in the first place. And that's really because it is finding all these ways in which words are like each other and sharing, right? Making use of the existing structure in the dog to add new words without adding bulk. So once I've done this, I have to say that I've made the data structure even less flexible. So to be clear, each of these steps, right, has a cost somewhere else. It made the code more complicated. It also made it so that now that I have all this sharing back here, that when I'm adding in a new word, so if I go back to look at this picture here, that I go in to add a word and I say, oh, actually the word, portioning is a word. Well, adoptioning is not, right? And so that will necessitate, if I go in to add the word portioning, that I actually have to split it off of its existing unified branch, because if I just tacked on the ing on the end of portioning there, then it turns out that adaptioning and adoptioning would suddenly become words too. So actually I have to be extra careful once I've got it unified this way, that when I add new words that I don't actually accidentally add some additional words that I didn't plan on, because these paths have been shared. So it requires a little bit more careful management. Again, the goal though here in this case was to try to build a data structure that once kind of freeze-dried. So I built it off the data structure, the input data file I had, that then would operate very, very efficiently. And I wasn't planning on making a lot of runtime changes to it. So I get this down to this. And then the last thing I'm going to do to it is go back to kind of the CS side of it and see if I can squeeze it down kind of in terms of just data structure, what's being stored per node. So I have 80,000 of these. So typically when you look at a structure, right, it's very rare that the idea, if you change something from an int to a car, right, so that was a 2-byte thing into a 1-byte thing, that you're going to have any profound impact on the total size needed. But if you happen to know you're going to make a lot of these structures, tens of thousands, right, almost 100,000 of them, then it turns out every byte counts. If I can get this thing down from, in this case, 10 bytes to 8 bytes, or to 6 bytes or 4 bytes, right, then it will cut my memory, right, by quite a factor here. So what I did in the final version of it is I used a little technique called bit packing, which is to actually stash stuff in the absolute minimum possible space that I can fit it into, taking advantage of things like, for example, that there are only 26 letters in the alphabet. A character is actually a full 8-bit value, which can hold numbers from 0 to 255, and I just don't need that much space. I'm not using the yen sign, I'm not using the parentheses, I'm not using the digits. So having, in some sense, the capacity to store all those distinct characters is actually a cost I'm paying on every character that I don't need to. So in fact, I squeezed it down by dividing up into the sub-bit level. This is something that's talked about a little bit in chapter 15 if you're at all curious. It's not what I consider core material for 106B, but I'm just sort of mentioning it to kind of complete the picture, where 5 bits, given that a bit is either 0 or 1, that I have 5 of them connected together, then I have 2 to the 5th different patterns that I can represent in that amount of capacity there, and that's 32 different patterns, which is enough for my characters plus a little slack. I use exactly 1 bit for is-word rather than a full Boolean. All I need to know is yes or no. I also changed the way I did knowing that you were the last child of a generation. Rather than having A say, there are 12 children here, I just said, go to index 27 and start reading, and one of them will tell you it's the last. So each of them says, no, I'm not the last, no, I'm not the last, and then when you get to the last one, it will be marked as yes, and that's how you'll know that's where A ends and the next one begins. And so if I can get it down in this way, I've taken what was a 10-byte structure down to 4. And it turns out there's often reasons why trying to get it down to a multiple of 2 is actually a critical barrier. That if it were 5 bytes, it's actually likely to be 8 just because of what's called alignment and padding restrictions. So if I were at 7 and I squeeze it down to 6, it might not make any change. And if I squeeze it down to 5, it still might make any change. It might be actually artificially deciding that each of those structures is going to be 8 behind the scenes. But getting it down to 4 actually tends to be another one of those critical barriers where, okay, 4 actually will be smaller than something that was 10. And so I take my 80,000 nodes, I get them to be 4 bytes each, and then I now have a data structure that's about 1/3 of a megabyte in memory, as opposed to the over a megabyte on disk in the text form. And so that's how it does what it does. So if you go and you look at the code, right, you'll see that there is this complicated bit-packed structure that it does look for things kind of by using a recursive character-by-character strategy of start at the top, find the matching character, then go to the children index, and then work your way down the children to find the next matching character, and so on to find its way through the data structure. So 25 bits is just where is that with a child index. So for example, the idea that A says my children start at 27 or B starts at 39, and so I just need a number there, but I'm using a slightly smaller than an integer just to make them all fit very tightly. So I'll tell you a couple interesting things about it actually before I close this off, which is the lexicon.dat file actually just is an in-memory representation of what the dog data structure looks like. And so in fact it's very easy to take the whole data structure. It doesn't have any pointers in it. Pointers actually tend to be a little bit, make data structures harder to rebuild and to dehydrate to disk because they have to kind of be wired up in memory. You don't know what memory you're going to get from new and what the addresses are. This one actually doesn't have any pointers. Everything is actually kind of self-contained. It's just one big array of these blocks. And all the information is relative in there. It says go to the index 27, index 45. So you can take that whole block and just write it to disk, 300 bytes worth, read it back in 300 bytes worth, and it kind of is rehydrated without any extra effort. So that's actually what the lexicon.dat file is. It's just a dehydrated form of the dog having been built in memory. So that makes it very, very fast to load. At that point, though, it's super inflexible. If you want to add a word to it, right, the way the structure is built, you'd have to kind of add nodes and make sure it wasn't glumming onto some existing words that were nearby. And so it would be a lot of work to actually edit the dog in place. In fact, when you ask it to add a word, it actually doesn't edit that one at all. You say, I'd like to put a new word in. It says, this one's so perfect the way it is. I've built this one, I love this one, I'm very happy with it. If you want to put some other words into it, it just keeps a second data structure on the side, an auxiliary one over here, where it sticks the additional words you ask it to put in. I have to say that seems like a very obvious thing to do, but in fact, I didn't even think of that for years. Right? We had the lexicon, and I said, well, you can't use the lexicon to make new word lists or edit them. You can only load this one beautiful, perfect one. You can't do anything else. And at some point, people kept saying, I wish I could put some words in the lexicon. I wish I could use it for the word list to keep track of the human and the computer players. And I'm like, well, you can't do it. You don't understand. It's very complicated. You just don't understand, my pain, right? Whatever. I had excuses. And then really after some number of years of just being a baby about it, I'm like, oh, of course. Why don't I just keep another structure off to the side? It's an abstraction. It's a word list. You don't need to know what I do. The fact that I keep a dog for some of the words and just an ordinary set for some of the other words is really completely irrelevant, right? And as long as when you ask for words, I look in both and I tell you, yes, it's there, why do you need to know where I keep it? Okay, so it took me a while to buy abstraction, even though I teach it all the time. It just wasn't totally making sense. So a neat little thing, just kind of keeping both behind. And so it turns out that I learned about this actually from a paper that I read at the in the early 90s about somebody building a Scrabble player, and they wanted a dictionary that supported kind of finding plays on the board and being able to extend words. And so knowing things about root words and how they extend in prefixes and suffixes was kind of the original motivation. And this kind of data structure is actually really great for any kind of word playing. So you have anagrams that you want to rearrange or words you want to extend past suffix and prefix, that this kind of data structure is really optimized for doing that kind of traversal and kind of leveraging the existing patterns in words to save space while doing so. So it was a really fun little project to do. It was kind of neat to think about. And even though today, if you needed a lexicon, you could just use a set. It's fast enough. It takes a ton of memory, but you know what? Memory's cheap. So this is not the kind of thing you would need to do today, except when you were in some kind of embedded, low memory, very, very tight processor environment. But it still makes for kind of interesting sort of artifact to think about how you get there and what kind of things you can use. So Wednesday, we will talk about some big picture design, kind of some wrap stuff, and I will see you then.
You will never have it.